Hello and welcome to today's office hours. Today we are talking physical testing and field testing. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. If you are unfamiliar with our office hours format, it is a shortened presentation, usually 20-25 minutes, and the rest of the time is yours. If you have any questions, concerns, issues that you're seeing with your physical or field testing that we can help with, simply drop it in the chat. That should be located in the bottom right-hand corner of your screen, and we'll have a good discussion there. We are also recording this, so immediately following the presentation, you'll receive an automated link with this recording. Feel free to, share it with colleagues, take screenshots, whatever you need, and also know that after the fact, if you do have questions, you can simply hit reply to any of the marketing messages. It'll come to my team and we'll route it to the right technical specialist in your area. Our speaker today, don't forget to unmute yourself there, Noah, is Mr. Noah Morgan. He's one of our applications specialists, and he'll be taking over here. How you doing, sir?
Good. Here I am.
Here you are. All right. Great.
All right. Okay, so yeah, like John said, today we'll be going over some of our physical test instruments and our field test kits. Yeah, we'll talk about when to use them, what industries they're most useful in, and then how they're run through. So without further ado, we'll dive into our first instrument of the day, the fineness of grind gauge. So grind gauges are another one of the instruments that we offer for a physical test line. A fairly simple instrument. They determine the fineness of grind. For background, the fineness of grind of a coating is expressed by the size of the pigment and the extenders it contains. So the size of these particles depend on the degree of grinding. Therefore, the determination of the fineness of grind serves to evaluate the appropriate amount of grinding in the production of coatings. So with this test, you can find out, if you change the dispersion process, if you start to disperse for longer periods of time versus shorter periods of time, you'll see changes in your fineness of grind. Maybe your particles will get smaller, they'll get larger, depending on what the process is and what the material is. But for the most part, it just serves to identify what the particle size is in your material. So you run the test by applying some of your material in the lower portions of the gauge, and then using a straight edge to slide it up the gauge to then determine what the particle size is. And you'll see the particle size line up usually where you have the most agglomerates, and then you'll determine that and verify and essentially just describe your material as that degree of fineness. So fairly simple test there. Next we have up is the density cups. So with density, it's another fairly simple test, and it's used to define paints, similar liquids, oils, usually things that are being poured because they have to have a certain density. The test is run by basically weighing the cup to identify what the weight of the tear is. Then filling that container. This container has a known volume, and then you run a calculation with essentially the values of the empty tear or the empty container with the weighed container, and that gets you your density of your material. So another fairly simple test used in the coatings industry, inks, pastes, some food products as well. And sometimes it's even used to indicate the purity or the quality of raw materials. So a variety of applications, but the density cup serves a pretty good purpose and gets us good information on a variety of different materials. All right, next up we have our adhesion tester. This is our Gardner scrub. Adhesion tests are another offshoot of physical test. You can have a variety of different types of adhesion tests. You can have scrub testing, washability tests. And these instruments here serve several of those purposes. You see in these examples here, we have washability tests taking place, determining how much abrasion or abrasion resistance this coating can withstand. Some other tests that this can run are similar for windshields. So some windshields undergo testing, specifically with that wiping and that wiper blade that goes over the windshield and the coatings on that windshield. Test wearing again, and some effects that can happen if you have dirt or other debris that gets stuck between that windshield blade and the windshield itself. So some tests that go off of that. Just a variety of different abrasion and scrubbing tests that this instrument can perform. To run a test, it's fairly simple. First, you identify what procedure or standard that you'll be using. And then, like I said, we have many different accessory kits that can go with whatever test that you need to run, whether it's for windshields, whether it's for coatings, both architectural and interior decorative coatings. We can get that kit. Then once you prepare your sample based on that standard or that test method, you simply apply what materials are needed, whether it's a sponge, a scrub brush, that actual wiper blade that I mentioned, set the amount of cycles, the speed for the scrub, and then you can run the test for a certain duration of time. And then once you run that test, you can observe the panel change, whether it's a measurement that you actually take place over top of the sample to the color, or if it's some other type of metric. Moving on to some other instruments. So these are wet film thickness gauges. So serve a very simple purpose of determining the approximate wet film thickness of a wet surface. So a lot of contractors or applicators will have these, and it's just used to quickly gather, important data on what's happening with your application. So, for the example of a contractor, if they need to put down a certain amount of material, let's say on a roof coating, they can quickly take out one of these gauges. So on the left here, we have some in-mount gauges. They work by having an eccentric wheel in the middle where you essentially roll it over a surface. And the middle wheel will then pick up some of that liquid or some of that paint to a certain point. And as it goes eccentric from the outer wheels, we start to see a point at which the middle section has paint and the outer ones do not have any paint. And then we can see how thick that wet film is, that wet coated material is. Same is true for these gauges over here, these comb gauges, where you essentially just stick it perpendicular into a surface. And then you look at the markings, these little combs, and we see here that there is coating on the number 2 comb here, but not on the number 3 comb. And so in that case, we would say it's between 2 and 3. I'm assuming this would be mils. We could say the coating is between 1 and 2, or 2 and 3 mils. So pretty simple test equipment, just meant as a quick visual check and verification. Make sure you're following the right specifications and guidelines. Next up, for destructive film thickness, we have a Bico cut. This is one of our instruments that we use for determining destructive film thickness. So with it, you can figure out multiple coatings, if you have multiple layers, how thick each of those layers are. But then again, it is a destructive test, so it's going to destroy that sample. How it works is you have different cutters on the bottom of it that you can spin and decide which one you want to use. These cutters are based on standards, which say that if your coating is between this thickness, or we have the example here on the screen actually, for cutter number 1, if your maximum thickness is 2,000 microns or 80 mils, then you use that one. And you use cutter 2 if it's less than 1,000 microns, cutter 3 if it's less than 200 microns, And what we see is that they each coincide with an angle, and that angle is used in the calculation to determine the true coating thickness when we look through the microscope. And so how it's used is we just drag this apparatus over a coated surface, let's say a little test panel. It's going to scratch into the surface. And then we flip it over and we use this microscope. So this gray tube here is actually a microscope that's illuminated through an LED light that's right here. And you can actually read based on a scale. It's either metric or imperial, depending on the model. And you physically measure the surface of the coated material where that cut was made, and you can figure out and measure the individual layers. And then run it through the calculation that gives you the true actual thickness depending on the angle that you use to cut it. It's a pretty interesting tool, pretty helpful. So if you want to go the non-destructive way, we have non-destructive film thickness gauges. This one here is our Pico test, but they measure your film thickness for ferrous and non-ferrous materials, so magnetic and non-magnetic metals. What's nice is that they also measure dew point, air temperature, and relative humidity. So during your measurements, when you're measuring for your total film build, essentially, once your material is cured, you can also measure the dew point, air temperature, and relative humidity. So you can measure all of those drying time metrics just to record maximum amount of information. You also have, similar to all the other film thickness gauges out there, you have a flip screen, which is usually pretty standard, pretty resistant probes, drop resistant casings, which is nice, multiple calibration points, high-low tolerancing, so you can set pass-fail on certain materials based on how thick they are. For on-the-screen pass-fail modes, essentially, statistics modes with up to 1,000 measurements that you can save. Also continuous measurements for large parts, so you can hold down the measurement button essentially and go over the entire surface to get your values. So pretty helpful piece of equipment, especially for determining that film thickness on cured material. All right, so now we have viscosity cups. So getting into viscosity cups, these are cups that essentially measure viscosity through a standard method of having gravity define that force to have to measure your viscosity flow. So it's a metric designed around fluid flow. So for that defined geometry, we have defined volume with defined holes or orifices. We use gravity as that force that's applied to push the material through the defined hole or orifice. What we're measuring is the laminar flow, or we have a laminar flow requirement, but we're measuring the efflux time in seconds. So as we fill up the cup, we let the liquid flow, and as that material flows, we time it until we get the first break from that laminar flow. And with that time, we can then convert that into kinematic viscosity. So we'll be measuring that in centistokes. So based on the cup geometry, the orifice, the time in seconds of the flow, you can determine your viscosity in centistokes. We also have an app that can calculate this for you. It's pretty helpful, pretty nice. Where you essentially just pick out what cup that you're using, you enter the time that you received or measured, and then you get your viscosity value in centistokes. It also works vice versa. If you have your viscosity and you're looking for time, you can use it that way too. Pretty helpful. So keeping with the theme of viscometer, we have a new product here. So a couple years old at this point, maybe 2 years, but we have our Visc RT rotational viscometer. So this instrument, part of our rotational line, but we have multiple ranges from low, regular to high viscosity materials. So think of things like the viscosity of water, the viscosity of honey, and the viscosity of pastes or caulks you could think of. So very high viscosities you could reach with this instrument. Touchscreen, color display, so pretty helpful with user mechanics. You go through a pretty nice menu operation, and for test methods, it's pretty simple to set up. But yeah, very simple piece of equipment there. And then next up with that, we have another new product, which is pretty new, and it is more new than the rotational line, which is the cone and plates. So these instruments work very similarly, except that they base their measurement on a defined cone and plate method, where it uses a cone angle to apply a certain shear based on the speed to that fluid or material. With that, you can measure your viscosity. But you have 4 different models with this: a light premium, a light low. We have premium high temperatures, premium speeds. So our light low temperature model goes from 5 to 75 Celsius. So for typical, let's say, room temperature applications, with your 2 different models with that, your light and your premium, you have 4 speeds with the light and freely selectable speeds with the premium model, which means you can test different shears for more, let's say, R&D applications. With your light high temperature model, you have the same aspect there, but now you can go up to 235 degrees Celsius, so pretty hot temperatures there. So from 50 to 235 is your full range. And then lastly, multiple standards for your viscometers with this instrument. You have your ISO 2884, you have ASTM D4287, D7395, and then lastly BS 3900. So a couple different standards that these conform to. Always reach out to us. The reason for that is we do a lot of feasibility studies just to make sure which, let's say, viscometer is best for your type of material, whether it's for an R&D application or a quality application. Usually sending in samples to us will help us and help you define a certain test method or instrument to use in a certain situation. So it's a helpful piece of guidance that we offer with our instruments. All right. So moving on here, we have our protective coatings field test kit. So this is a test kit that we offer that comes with a thermo anemometer, so something that measures our wind speed. So let's say we're taking a coating or we're applying a coating on a roof. And it's important to know what type of drying situations or environmental factors are out there. So with an instrument like a thermo anemometer, you can measure the air speed, the relative air speed with the wind speed to determine some of those drying temperatures and drying factors that'll take place. And with that, you have a moisture meter, so you can measure relative moisture, both in the, let's say, the substrate, whether it's wood, concrete, metal. With that, you have dry film thickness gauge. So you can measure each of these aspects as you're both applying, but also inspecting afterwards. With that, you have the infrared thermometer. So another piece of instrumentation to use to figure out what your expected drying time is going to be. So diving in each one of these, we have our moisture meter up first. So our M100 and our M200. So it verifies moisture content of the substrate to determine the readiness for coating. So I mentioned earlier, works on a couple different substrates. We have wood, plaster, masonry, gypsum, concrete. So a variety of different hard substrates. But the idea is that you essentially poke the 2 probes into the, say, a wood, and they're measuring based on conductivity. So it's essentially a conductivity meter. And as you can imagine, if there's any type of liquid or moisture in that, it's going to be more conductive. And so that'll raise the moisture content. Pretty durable, so it has a hard protective case. So it's drop resistance, which is pretty nice for construction and scenarios along that sort. Getting into our anemometer, like I mentioned, measures the air velocity, air temperature, but also relative humidity. So good for identifying conditions that are right for painting. Calculation of dew point temperature, and it's also made of impact resistant materials like the moisture meter I mentioned earlier. So again, keeping the same idea of a pretty impact resistant material for construction environments. All right, and then here we have our infrared thermometer. Measures the temperature of surfaces to be coated. So laser targeted, shows the precision location of the temperature measurement. Pretty simple, pretty standard piece of equipment here. Just measures your temperature, has a laser built in so you can aim exactly where you're going to take those measurements. All right, and save the best for last here. This is one of our new acquisitions, the Pelt Ultrasonic Film Thickness Gauge. So for applications where film thickness is very important, specifically for, you could say like inspections, situations like that, for protective coatings where things start to play more of a functional role, not just for a decor or decorative role. This instrument is able to simultaneously measure up to 5 different layers by using high frequency ultrasound. So it works differently than the other film thickness gauges that we talked about or that I showed here. But this one can determine accurate film thickness of multiple layers on a variety of substrates. So not just metals, but also rubbers. You can think of composites, woods, concretes, metals, non-metals, all sorts of different substrates. But it's a pretty helpful piece of equipment, not just for inspections, but also for quality control and for research work. When you need high accuracy for multiple layers and not just total film build. All right, so with that, we'll go ahead and hand it back over to John here, and we'll get to questions.
Yeah, lots of good stuff, Noah. Thanks. And yeah, that Pelt thing is pretty cool. And of everything that Noah went through, the Viscometers and all the other physical testing equipment, if you don't see it in the BIC brand, always check out our Guardco brand. They have, way beyond what the BIC brand offers too. So if you're looking for any kind of physical or field testing equipment, it's in one of those 2 places. So yeah, if you have questions, drop them in the chat. Have a couple here. We'll just dive into it. What factors drive the choice between destructive and non-destructive film thickness measurement methods?
Ooh, good question. So, off the bat, a couple things come to mind. One of them would be, what is the sample worth? In the case of, let's say, a car, at that point, you don't want to go destructive because if you think about it, if we're going to test, let's say, the film thickness of a door panel. Yeah. In the case of a car, we have to throw away an entire door panel to test that film thickness destructively versus a non-destructive test where we can keep that door panel. So situations like that are one of the key points of when that idea becomes necessary. Okay. Yeah, it makes sense. You don't want to destroy a whole panel if you don't have to. Right. Are there pros and cons? Why, if cost isn't an issue with the sample, is there a pro or con to use destructive versus non-destructive, or do they kind of equal out? I would say they kind of equal out. You could think of, at the end of the day, they're both going to get you pretty similar values. Okay. Destructive, you can always confirm and 100% verify that that is the true film thickness. Whereas there's always a sense of not full confidence using a film thickness gauge, even though you can verify and check things. You don't really know for sure. But at the end of the day, I'd say most of the decision cost comes down to cost, and then it's efficiency. Is it more efficient to quickly take a measurement, or is it more efficient to scratch something and then look at it through a microscope? Because that kind of adds in a little bit of subjectivity to it. When you're looking through a microscope and identifying, is it 23 or 24 microns, right?
Yep, exactly. Next one, how would I ensure lab viscosity measurements to correlate to real world application performance?
Interesting question. So say that one more time.
How would I ensure lab viscosity measurements versus how they correlate to real world performance, application performance?
Right. It depends on what you're looking for. So if you're asking something like how could I say if I'm running a test with a viscometer, let's say, how that relates to something like using a brush to brush on a material to a surface. So in that case, that comes down with you start getting into the mathematics of shear with viscometers. And all a viscometer is doing is it's setting down these defined conditions at which a fluid is behaving. And so if you're able to, let's say, correlate or match an activity or a movement to a shearing force, the example of a brush moving, up against a coating and applying it to a wall. If you're able to get that piece of math, that shearing force that's applied to the material, you can then use a spindle with defined angles, and then a speed that the viscometer can run at, and then with that combination, get that same exact shearing force that you use to apply that coating with the brush.
Nice.
And in theory, if you know that exact force and you then use that exact force, you can get the viscosity behavior under those conditions. So that's one of the cool ways of once you're able to really dive into viscometers and their capabilities and material flow, you could really lock down an application with the R&D side of knowing how it behaves under all these conditions, and then locking down the quality control aspect of using these same conditions to match that measurement and make sure this, let's say, wall paint is always the same viscosity to the user with every batch.
So it's kind of like what you described with the viscometer. It's kind of like our scrub abrasier. You're simulating that real world application, and just to make sure it will, the material will perform.
Yep, 100%.
Cool. That's cool. I didn't even think about that for the viscometer, but that's a great way. And like Noel mentioned earlier too, for everyone listening and watching, if there's questions, get with Noah, get with any of us, and we'll route you to Noah and his team, and get a sample in, and they can run it through the riggers in the office in our lab, and make sure they're locking in the right instrument for you based on your sample and your material. So okay, let's see, what else do we have here. When working in the field, which is most critical for preventing rework? Moisture, film thickness, or temperature, and why? So this is getting to the field test kit stuff.
I always hear that moisture is one of the worst things to have, because once that moisture is behind that coating, it's the bubble, it'll spread, and it just makes everything worse and worse. So no matter what your film thickness is, what the temperature was, if there's moisture behind it, it's going to destroy things.
It's that humidity.
Yep.
Okay. Good answer. Do you have tips to keep your testing aligned with ASTM or ISO standards without, disrupting production?
Tips for following those. I would say first step is to look at the standards that go around them.
Yeah.
Once you establish what those standards are and read into what instrumentation or what requirements are needed, to make a good list of those things and then follow through with that. And usually what you'll find is they'll include test kits similar to these or recommend instruments or like we spoke of temperature, humidity, things like that, things that you can gather metrics on. Then it's just a matter of going out with that equipment and taking the measurements and recording them.
And locking down your process.
Locking down that process.
Right. That's the biggest thing with whether it's a physical test equipment or color and appearance. If you, if operator A is doing one thing and operator B is, slightly different, you're going to get different values and get different numbers. So can't emphasize that enough. Are there other, as you get samples in for testing and running, are you finding things that are continually causing issues for customers as they're sending their stuff in? Is there something frequent that you see over and over that you could share with the folks so they can hopefully prevent it in their facilities?
Yeah, for physical tests, not so much. So much, but I'll reiterate some cool piece of information or good information is the idea that having someone go in and preemptively study the rheology of your material and go through and find out what metrics are the best for testing, like the ones that provide the most valuable information, the most accurate information, and provide an efficient type of test is a very key commodity, especially when getting into the world of rheology with material that you're developing, especially for quality control. So that's something that we offer, and it's a very good resource to have and take advantage of because we can go in and really accurately define what's needed for that very specific application and then customize a solution for it. So definitely something to take advantage of if you need it.
Yeah, definitely. Is things like the BICO test, and integrating like an instrument like that into someone's quality control process, because like with every measurement we can get the data out of here and integrate it in the quality control process and that's going to help with warranties, rework, things like that when there's questions out there. Is that an accurate statement?
Yeah, 100%. So if you're able to, for thickness, for example, if you're able to go out and inspect and take these thickness measurements and guarantee to a customer of yours that you 100% put down, let's say 10 mils of material on everything. And then they have failures down the road and they cannot go back and now say that it's because you didn't put down enough material. That's written down that you did. So that's fine. Everything's written down. So you're no longer liable in that case.
That data is going to, protect your backside down the road, and then, just to ensure that it was properly applied under the right environmental conditions. And, maybe it's the coating, maybe it's another issue that's causing that, but it'll, protect you if you're the one laying down the coating.
Right. At the end of the day, these are all just tools that could really help you. And some can be more key and some can be less, but they're all tools for the key to success.
Yep, exactly. So what other questions out there does anybody have? Drop them in the chat thing. Quiet group today. What else do you see out there NOAA as, kind of the, people plugging into their quality control processes? In terms of instruments, is it like the Bico test that you have on the screen here, or are there other things? And I mean, that's a pretty wide question because it's totally dependent on the sample or what material you're running. So good luck with answering that.
Yes, I would say these field kits are very good for exactly what they're advertised for, being a field kit out in everyday use for contractors, applicators, things of that nature. They have quick and dirty tools for film thickness measurement, moisture measurement, environmental condition measurement. So quick and easy, quick and dirty, and they get you what you need. When you get into instruments like for cone and plate viscometers, rotational viscometers, then you're getting more scientific in what you're trying to define or research. And at that point, you start getting, like I said, more detailed into what you're looking at. So these are used more in laboratories. I wouldn't say this is something you can keep in the back of your truck.
No, definitely not there.
Yeah. So these are meant to be stationary in the laboratory, so you can run studies on materials. You have things like your dip cups, which can be both. I could say that could be a quick and easy test for on-the-go things, but not so much just because the temperature. Temperature is a big factor in viscosity, but you could in a case be just because it's so small. But laboratory indoor on-the-go use for quick viscosity measurements. But that's mostly what you'll find with physical tests. It's you'll find things that are for quick and dirty testing, but you could also get very deep into the physical realm of fluid mechanics or physics,
rheology,
rheology and things like that, right?
Yeah. Okay.
Yeah.
Go ahead.
I was gonna say that another thing is things like the scrub tester. This is a pretty interesting piece of equipment because of the versatility of it. You can go from something, like I mentioned, this picture down here being a washability test to see how washable or scrub resistant that coating is, to things like testing the scratchability or scratch resistance of windshields with, wipers being exposed to a certain type of dirt and dust. Things of that nature. So a lot of things can test not just the durability, but how well it can hold up over time against this, how well it can scratch and cause these other aspects and like haze and clarity issues.
Mm-hmm. Yeah, you make a good point about, just if you're distributing, nationwide, you want to test it in the cold, near the coast where there's salty air, salt water, out in the Southwest where you get the dry temperatures and the dust and dirt and things like that. And run it through the gamut there. Yeah. Mm-hmm. Another question here: what effect does UV rays have on destroying film thickness, or do they help facilitate the degradation?
Yeah, great question. I think it's strongly dependent on the type of coating, but UV can play a role in coating degradation over time. Like I said, very dependent on what it's made out of. Some coatings are UV resistant, some are not. If you get into the color of it, as fluorescence starts to decay, will start to change color over time. So that's when you'll see like a deep red or a very vibrant looking red over time that's exposed to UV light will start to slowly turn into a really dull red. Something that's not vibrant. So,
will that also affect the actual film thickness of the coating?
I think theoretically it's got to in a way. I think it's very small. Again, if you have a lot more of that material that will decay in UV, you might notice a change that is pretty significant. I have to say.
And you're the technical expert, but I would think that you're going to first notice the color appearance and gloss starting to degrade before you even get into the film thickness measurements. And again, it's dependent on the industry and what coating or surface you're running.
Yeah, definitely depending on what it is, but for sure, yeah, I think you'd visually notice it first, and then you might see that physical difference as well.
Yep, exactly. What else, folks? We got Noah here. Anything else we can help with while we're here? And I think this topic's always one of the shorter ones. People, don't get into, I guess, as much field testing maybe, or a lot of the instruments too are so easy to use, self-explanatory. There's not a lot of things you can do wrong.
It's true. Out of all the presentations, this one has one slide per instrument.
Right. You're not getting into the color science and equations and all that stuff here. So let's see. Any final tips? I mean, if there's no other questions, and everyone's busy, and no need to hold you here if we don't have to. Any final thoughts on just the topic of field and physical testing, Noah?
Yeah. In a world of coatings and coating technology, we all focus a lot on the color aspect, but the physical aspect, the functionality of coatings is another very important thing, and that's all made up of the key factors of, again, your environmental conditions that you're applying and coating in, which can be tested for, but also what are the fluid mechanics. So all of these physical properties, you always have to look at multiple levels, and for this one, it's color, so the appearance of your product, but also the physical aspects of your product, which a lot of instrumentation can test for. So it's important to use it if it's there.
Yep, absolutely. Good point. All right, with that, I think we'll wrap it up here. Like I said, you'll get a copy of this recording in your email. If you think of any other questions later today or next week or next month, you can hit reply, and we'll route it to Noah or someone on his team and get those questions answered for you. So thanks for joining us. Thanks, Noah, again, for sharing your expertise with us. We appreciate it, and have a great day, everyone.
Take care.